This is Brady Johnson to do presentation number 2. So before we start with part A, B, and C, I first want to add a resultant torque at point A. And so why we have that is because we have 75 pound-feet going in counterclockwise direction at B and 50 pound-feet going clockwise at part C. So what we know from here is in order for this to be in equilibrium, which we always assume it is, then we have 25 pound-feet at part A, which would be the resultant torque. So I am drawing this right there. TA equals 25 pound-feet. I apologize for the red pencil. I don't have a red pen. But starting from there, what we can start with is a torque diagram. So we draw that. This is on. And so we have, this is the X direction. So what I'm gonna do for the remainder of the time is I'm gonna convert all of our torques into inches because that is what we're gonna do our calculations in instead of going back and forth. So I wanna start right immediately at the torque diagram just so we don't have to mix and match between numbers. And so this is gonna be in inches. And then we're gonna have our torque in pound inches. And so since we're starting at the fixed end, we're gonna start with the torque from A. So we're gonna start, since it's in a clockwise direction, the resultant torque is gonna be a positive because it's reacting. So we're gonna start with positive 25 times 12, which is gonna be 300 inches, 300 pound-inches. So we're gonna start here. We're gonna mark 300. This is at part A. That goes to part B, which is about 3 inches, so it's 3 feet, so it's a little bit longer. And part C, which is 2 feet, so it's gonna be a little bit shorter. So this is gonna be here till about part B. And what's that's gonna bring us is to part B, which is 75 pound-feet, which if you multiply by 12, then you get 900 pound-inches. So it's gonna go 900 pound-inches downwards, which doesn't mean it's gonna be at 900. Rather, what it means is it's gonna be at, I gotta make that better, negative 600 pound-inches. So that's gonna drop. There's the straightest line I can give, and then that's gonna go on until we get to part C, which is 50 pound-feet, which if you multiply by 12 inches is gonna be 600 pound-inches. It's gonna bring us back to 0. And so this distance right here is going to be 36 inches. This distance is going to be 24 inches. So it's just something to keep in mind for the calculations that we have later. Other things to mention is we could see just through equilibrium that if we're trying to find the deformation in C, which is going to start for our part A, if we're trying to find the deformation in C, we can tell that for the deformation in C, it's going to be the deformation we have in part AB plus the deformation we have in BC, because that deformation at the part C is our resultant, which adds up all of ours. So we're going to have psi AB plus psi BC. Another thing that we could see is that we know within our BC range, because we have aluminum core that's wrapped around in a cylindrical steel. And so what we do know as well is the whole entire torque in BC, which would be this area with the core, is going to be the torque within that aluminum plus the torque within that steel. And that's similar to the other one because we know altogether to have the resultant torque that it's going to have to not just respond with one or the other, but have both together. So starting to find psi C, we're first going to find our torques of aluminum and steel. So how we can start is using our compatibility equation. We know that psi AB or psi BC of steel, so the outer core right here, equals psi BC of aluminum. And like I said, because they're going to have the same exact deformation within here. And so when we have find our deformations, we know the equation for deformation is our torque times length divided by J times G. So now's a good time to input on the side. We're going to have our G, which is our modulus of rigidity of steel, equals 11.2 times 10 to the 6 psi. Our modulus of rigidity for aluminum is going to be 3.9 times 10 to the 6 psi. Those are numbers we'll keep here for future keeping. So we're going to start here. So using this equation for both, we're going to find the torque in steel times its length, which they have the same length, so it's not going to have its own underneath for it, times the J of steel times the modulus of rigidity for steel equals the torque for aluminum times that same length divided by J of aluminum times the modulus of rigidity of aluminum. One thing we could immediately see is that we already have a variable we can cross out, which is our length. The others, though, are different, so we're going to have to compute them. The torque of steel is going to be J times G of steel. Well, let's find what J of steel is. J of steel, because there is a core on the inside, we're going to have to find the outer diameter to the fourth minus the inner diameter to the fourth times pi over 2. So how that's going to look is pi over 2 times r outer to the fourth minus r inner to the fourth, which equals pi over 2. Our r outer is just 1 inch, 1 to the fourth, minus our inner, which is 0.5 to the fourth, 0.5 to the fourth. This gives us a J of steel, which equals to 1.4726 inches to the fourth. Let's just give that a little emphasis there. Cool. Now we're going to have our J of aluminum equals, because it's just a circle, we don't have to have the outer radius and inner radius. It's just going to be pi over 2 times the radius to the fourth, which is going to equal pi over 2 times 0.5 to the fourth. That gives our J of aluminum to be 0.09817 inches to the fourth. We're going to box that up as well. So now we have right here torque of steel divided by the J of steel, which is going to be 1.4726 inches to the fourth. Oh, there we go. Times the G of steel, modulus rigidity, 11.2 times 10 to the 6 psi equals the torque in aluminum over the J of aluminum, which is going to be our 0.09817 inches to the fourth, divided by 3.9 times 10 to the 6 psi. There we go. And I want to go back really quick. I wanted to, just for organization, before when we go back and forth, this is going to be our equation 1, and we're going to keep this as our equation 2. Cool. And so we'll go back to those, and so I want to keep that for safekeeping. We're going to push this forward, pull a new piece of paper out, and by computing these numbers right here, there we go. That's a good place to put it there. We find the torque of steel divided by really big number. We put it like that because that's how my calculator has it. Equals torque of aluminum divided by really big number. To isolate the torque in steel, we just multiply that over. We get the torque of steel equals 43.078 times the torque of aluminum. This is going to be our equation 3. So now what we're able to do is we're able to input this this variable, torque of steel, what it is, and then we're able to put it into our equation 2 right here. So when we do that, we get, instead of torque of steel, we get 43.078 torque of aluminum plus torque of aluminum equals torque of BC. What we know though is the torque of BC is going to be our 50 pound-foot, which is going to be 50 pound-inches right here. So our negative 600 pound-inches. We can see it through the diagram, but we also see it through our torque diagram. That shows us, that gives us actually the best visual on finding that number. So we put that in equals negative 600 pound-inches. Now, by combining these together, you'll get 44.078. Divide that over, we find that the torque of aluminum equals negative 13.612 pound-inches. So we're not done yet. Now we need to find the torque in steel. The torque in steel is going to be that equation number 3 that we had. It's going to be this number times 43.078. So it's going to equal equal 43.078 times our torque of aluminum that we just found. Negative 13.612 pound-inches. So we find that our torque in steel is going to equal negative 586.388 pound-inches. So we're going to now hold on to that. So now that we found both of these, what we want to do is find the torque in BC. So there's 2 different ways we do it. Both will result in the same answer. And so what we do is, deformation of BC, not the torque of BC. We're trying to find the deformation of BC. There's 2 ways to do that. And so one way to do it is to go back into our equation right here and just use one of the materials to find the answer. Both different materials, when using those numbers for it, will find the same value, and I will show that. So to find the deformation of BC in steel, we're going to find that using that torque of steel times length over J steel, the modulus of rigidity of steel, that's going to be the equation to use. We're going to have all the same values for steel. So that's going to have us find the torque of steel, which is going to be negative 586.388 pound-inches times that length. Well, that length of it is going to be 2 feet, otherwise our 24 inches that we had in our torque diagram. So 24 inches. And then we're going to divide that by our J that we found right here, our 1.4726. 4726 inches to the 4th. And we're also going to divide that by the modulus of rigidity of steel, which we have at the top to be 11.2 times 10 to the 6 psi. There we go. And this yields the number negative 8.533 times 10 to the negative 4 radians. And so just to show that we're going to get the same answer, I'm not going to box that yet. We're going to have now the deformation of BC of aluminum, which will be the torque of aluminum times length divided by the J of aluminum times the modulus of rigidity of aluminum. That's going to get us to use negative 13.612 pound-inches. Same length, so it's going to be 24 inches, divided by that J that we found for aluminum, which could be right here, so 0.09817 inches to the 4th. And then our modulus of rigidity for aluminum here, which is going to be 3.9 times 10 to the 6 psi. And then when we do the calculations for that, we get the same exact answer. And that is our deformation in BC. So we're not done yet. So now going back into our equation that we used, our equilibrium equation we have the deformation of BC. Now we just need to find the deformation of AB to get our answer for part A. And so to do that, we now have to have deformation of AB, which is going to be the torque of AB times the length of AB over JAB, and then the modulus of rigidity for AB. That was ugly G. So the torque of AB, if we go back in our torque diagram, we're going to have 300 pound-inches. So that was that resultant torque that we have right at the point, right at the fixed end. So we're going to have 300 pound-inches times its length. As we put in our torque diagram, we have 36 inches for the length, 36 inches divided by J and G. So we're going to find the J right now, right below. J of AB, because it's solid, we don't have to have an outer diameter minus inner diameter, so we're just going to have a pi over 2 times its radius, which is going to be 1 to the 4th, which is just pi over 2, which is only going to be 1.5708 inches to the 4th. So now we're going to have 1.5708 inches to the 4th. And then the modulus of rigidity. And because it's steel, we're going to have that same 11.2 times 10 to the 6 KSI, or PSI. When doing this, we find it to be 6.14 times 10 to the negative 4 radians equals AB. So now we're going to go back to our equation 1 right at the beginning, which is going to be our deformation, deformation of C equals deformation of AB plus deformation of BC. Now that we have AB, we're going to put equals 6.14 times 10 to the negative 4 radians plus, since it's a minus sign, it's going to be a minus 8.533 times 10 to the negative 4 radians. Getting that, we find our psi of C equals negative 2.39 times 10 to the negative 4 radians. Or we could have it be negative 239 microradians. So that's part A. Now we're going to move on to part B. Part B asks the maximum shear stress in the aluminum. So that's going to be specifically and isolated to the aluminum core within section BC. And so in doing so, first we're going to write our shear equation, which is going to be our shear equals our torque times our C, which is going to be our longest radii length to the outermost fiber within the aluminum, which is going to be its radius, divided by J. So to have our T max, our shear max of aluminum, it's going to be our torque of aluminum times the outermost fiber divided by J of aluminum. And so in doing that, we get the torque of aluminum was right about, flipping to the side. Our torque of aluminum we found to be negative 13.612 pound inches. Negative 13.612 pound inches. To the outermost fiber is going to be our radius. And so for the aluminum, that's just going to be 0.5. And then for J, we find our J of aluminum to be our 0.09817 inches to the 4th. So we're going to have 0.09817 inches to the 4th. Getting that number, we find our shear max of aluminum to equal negative 69.33 psi. And that's our part B. So that one was a lot quicker. However, part C, we're going to have a little bit more to do. So for part C, we're trying to find the shear max within our steel. And so what we need to understand with our diagram is we have both steel from section A to B, fully steel, but we also have steel from section B to C that has an aluminum core. And so what that's going to mean is we're going to have a different torque, we're going to have a different C, and then we're also going to have a different J. And so that's why we have to check from both sections, and whatever number is largest is going to be our largest shear stress for steel. And so we're going to start off at section BC. There we go. For section BC, so T max of steel BC. Well, that's going to be our torque at BC of steel times the outermost fiber at BC divided by our J of BC of steel. and then I was about to add G, that's the previous equations. And so in doing so, we find our T of steel, our torque of steel, which we found earlier to be negative 586.388. That's a negative 8. Negative 586.388 pound inches times our C to the outermost fiber, which for our steel is going to be 1 inch, divided by the J that we found, which happens to be our 1.4726 inches to the fourth. 1.4726 inches to the fourth. Doing the calculations, we find that our maximum shear of steel at BC equals negative 398.2 psi. So before writing that, now we're going to start on our maximum shear of steel, oh Lord, at AB. And that's going to be our torque of steel at AB. It's just steel, so I'll just write AB, times C, which is our radius, divided by our J at AB. And so, in putting in the numbers, we're going to find our torque at AB through our torque diagram is going to be from AB 300 pound-inches, positive 300 pound-inches. Our outermost fiber, it's also going to be just 1 inch, just like section BC. So 1 inch, and we're going to divide it by J of AB, which we found to be 1.5708 inches to the fourth. And then in doing that math, there we go. In doing that math, we find that our maximum shear of steel at AB equals 190.98 psi. Because these are magnitudes, we find this number is smaller, and so that's going to give our maximum shear of steel is going to be negative 398.2 psi. Our maximum shear of aluminum is going to be negative 69.33 psi, and our deformation at C is going to be negative 239 microradians. Thank you. Oh, actually, signature time. I almost ended that video, which would have been awful. Signature to prove that I am me. Brady Johnson, right there. Thank you.